Okay, so last class, what we tried to do is we tried to motivate the following idea. So what was the idea that I was trying to motivate? Well, one fancy way is to sort of, well, I guess one fancy way of saying it is the following. Sampling distribution of the mean. So I'm going to try to give a more, what I did last class is I said, here's an example that looks very similar to some examples we had previously done, but there was one subtle difference. And that subtle difference is we were asking a question about the mean of some population, particularly taking samples of that population. And so what I did is I tried to stir your imagination a little bit. I don't know if it worked. Who knows? It's kind of hard to tell when we're sitting on computers. But what I tried to do is ask you questions and stir some things in your head, some old ideas. A while back, we talked about this distinction between sample mean and population mean, and sample variance and population variance, and how that might come to play. And then I also wrote a couple things about, some equations, some that we've seen before, some that we haven't, and I tried to maybe get you to think about where these letters or these variables or these numbers, whatever you want to think of them, where they come from or why they might be of interest. And I said behind all this is this big, powerful theorem called the central limit theorem, and it gives us a way to answer some practical questions. And we want to build to what that means, and also try to explain it in the language of this class, which, as I suggested before, sometimes that's hard to do because the language that most of this material is written in requires you to be able to read and understand calculus. And clearly, we're not expecting that most students, if any, in this class have any even familiarity with calculus. So we have to be very careful how we state these things, and we try to describe them for you guys to learn. So what I'd like to do now is sort of phrase a similar question that I did on Tuesday, but I want to kind of put it out in a little different meaning, maybe more words than mathy, and then we'll see if this is something that we can sort of pick up. So before we do any of that, does anybody have a question about any of this? Comments, concerns? All right. So let's go with the following. So imagine we want to, say determine the average height of adults in Pennsylvania. So this seems like a very basic idea. Who knows why you'd want to do this? I don't know. Maybe you're curious to see how tall you are compared to other adults. The first thing to note about this experiment is that this experiment is going to take quite a long bit of time. It might even seem impossible. So questions that might immediately come up: is it even possible? You know, one simple question is, how could we even account for every adult? Did we miss any? Okay. So as we sort of spoke to on Tuesday, then the question becomes, can we just take a sample of the population? So notice I'm using two words that we've talked about before. I'm going to put them in quotation. If the whole population of adults is what I really want to analyze, the question is, can I just take a portion of them? And then if so, how many do I need? Do we need 20? Do we need 200? Do we need 20,000? I mean, how many adults should we sample if we hope to get reasonable information? So here's an idea. Instead of asking that question, the idea is as follows. So one idea is, let's take a bunch of samples. What does that mean? Maybe we take 10, maybe we take 20. So what do I mean by that? So sample one, maybe we measure 30 random adults. And then sample two, measure 30 random adults. Just pick them at random, whatever that might mean. And then maybe we'll take, I don't know, we'll do this, say, 50 times. So we'll go up to the 50th one. So the idea is I can't measure everybody, so let me just take 50 experiments. In each experiment, I'll measure say 30 adults. And by the way, there's really nothing special about me doing this 50 times. And there's really nothing special about me picking 30 adults each time. Those are the numbers that just kind of popped into my head. And so that's sort of what I'm sticking with. All right, so here's what we find. And if I go to the next page. So what we can do is we can compute the mean of each sample. So we'll call them, there's 50 of them, so we'll call them the following. We'll call them let's note that they are random variables, so here's what we'll call them. We'll call them x1, x2, x3, all the way up to the 49th and then the 50th. Now, these are all means, so I want to make sure that we understand that. So x1 is the average of the first sample, x2 is the average of the second sample, x3 is the average of the third sample, so on and so forth. Does anybody have a question about this? Okay, so what can we sort of say? Well, there's what we have to do here is we have to take a leap of sort of faith. We have to have trust in sort of what I'm going to tell you. And I'm going to try to do my best to explain why that's the case. So we can take the mean of these guys. So we might call that x bar. What is x bar? Well, x bar is, there's 50 of them, so it's x1 plus x2 plus all the way up to the 50th guy, and then I divide by 50. Okay, so again, we have 50 experiments. For each one of those 50, I take 30 people, I measure their height. Then I find the average. So I have 50 averages. I have x of 1, that's an average. X of 2 is an average. X of 3, all the way up to x of 50. Now I'm going to add them together and take their average. Okay, so what we want to now think about is, what does X bar look like? I mean, that's a natural question. What should we expect it to look like? Well, in order to answer that, we need to sort of think about our population and how it relates to our sample. Now, in this particular quote unquote example that I'm discussing, let's make some assumptions that we might do if we were actually doing this study. We might say to ourselves, well, maybe we have some guess of what the actual mean is. Maybe we guess that the average height is blah. Or maybe we're doing a different experiment. Maybe we're doing an experiment where we already know what the population mean is, or the theoretical mean. So it turns out that if we believe this thing called the central limit theorem, tells us tells us this. So how does it do it? Well, we have to write it in a little bit of language. So it says, well, actually, let's just say it in sort of in an arbitrary way first. So it says, that this X bar that we compute should be approximately the theoretical or population mean. And it also tells us, excuse me, it tells us something else. Tells us It even tells us how the variance looks. The variance of the mean distribution, or let's just say the variance. Put it this way. So now we don't want to, we sort of don't want to say things that are incorrect. So let's be very careful how we say this. The variance keep forgetting to erase things. The variance will approach zero for large number of samples. So how many samples did we take? We took 50. Is 50 large enough? Typically, what we mean by large, oh my gosh. So typically what we mean, the standard that we typically mean, large means greater than or equal to 30. So 50 is greater than or equal to 30, so we should be getting good information. Okay, so what does this mean for us? So I'm going to back up for a second, because as someone who teaches this stuff, again, it's very difficult for me to try to explain this stuff in a way that is understandable right away, because it's difficult to learn. And to add more difficulty to this, as I said, I'm putting lots of things in quotation marks because there's not really a good way in my brain to write them down unless I use the language of calculus, which I can't use here. So typically what a book does is a book just tells you, here's a formula, trust us, you know, and I don't like to do that. I'm trying to give you at least a little intuition of what happens. And I think this is a good example to help you if you really think about doing this experiment. If you went and said, okay, I want to go get 50 random people, or excuse me, I want to go grab 30 random people, measure their heights if they're adults, and then have 50 other people do this experiment, you would imagine that you would have, okay, you have 50 numbers once you compute their means, and you say, okay, what's happening? Well, then what if instead of you doing 50, what if you did 100? Or you did 1,000? Well, what you're going to find happen is that if you do 100, and then you did 101 or 102, what you're going to find is you're going to find that your mean, you're sort of taking 100 was not much different than you taking 101, or taking 102 was not much different than you taking 101, and taking 103 different experiments would not be any different. And so in calculus, this idea is what's called a limit. You see this thing of a limit happening. And to really explain what all that means, if you really want to understand it, you're going to have to take some more classes in different levels. But intuitively, if you really spend some time to ponder this height example or something similar, you might get a better idea for what we're saying. So at this time, if you have a question or you want something clarified, please ask. Otherwise, I'm going to just give you the formula, even though I gave it to you last class, and we're going to talk about how to use it. So Okay, so what it really says is the following. So more specifically, the central limit theorem says the distribution of what we're calling the sample mean can be approximated with a normal distribution with mean mu and variance oh my gosh, sigma squared over n when n is large. So for us, large means bigger than 30. So this is a heavy statement, and it's kind of very wordy. And again, doing examples is one thing, but trying to actually understand it is a whole nother situation. Okay, so we know that before our z had a special, our z-score had a certain thing. It was x minus mu divided by the standard deviation. Well, the standard deviation is now going to be the following. So we'll have x bar minus mu, but it's not just over sigma, it's now over the square root of sigma over n. So this is that thing I wrote yesterday. And the reason it's true is because of what's called the central limit theorem. Now, if you think about number sense and some reasoning, it's not going to take you long to make something from this, but it's going to take you some time. We would imagine the more samples we take and average out, we would imagine that that distribution is going to become more and more resembling just think intuitively, would it resemble a normal distribution? And then we would also know that the more samples we took, that the variance would have to shrink. And so if you look at this formula for the variance where it's sigma squared over n, this is not made up. It's not that someone just says, let's call this the variance. This is something that can be derived if you have the appropriate tools. And once you derive it, it does make intuitive sense, because if you let n get bigger and bigger, what's going to happen? Well, go to a calculator and take a number and then divide it by large numbers and then divide it by even larger numbers. Well, what happens? That number becomes smaller. In fact, the bigger n is, the closer that ratio becomes to 0. Again, the larger n is, don't forget sigma squared is fixed. So if sigma squared is fixed, and we let n get bigger and bigger, the larger n is, the smaller this fraction becomes. And so that should agree with your intuition. The more samples you take, the less variance you should have. Okay. Does anybody have a question? Now, let me be clear on something about this. So the central limit theorem, you might ask, well, you keep talking how it should be written in calculus. And the answer to that is absolutely. So if you ever wanted to actually see the details of this, what you would typically do, if you would take classes in calculus 1, 2, and 3, and then you would take a class in probability and statistics. And then in your second class in probability and statistics, you would finally study this. So essentially, this central limit theorem is something that is, if you want to see it written exactly and derived exactly, you have to take about 5 more classes. But that doesn't mean you can't use it now. And so that's what we're going to do. We're going to use it. I mean, you know, think of it this way. I mean, pilots fly airplanes and not all of them know how to build an engine or how it works. You know, you drive a car all the time, but you probably don't know the first thing about how to build a car or how a car works mechanically. Maybe some of you do. So even though we don't know all the specific details to why the central limit theorem is true, why it works, where I came up with this equation, what you can do is you can trust that you can use it to answer questions. And we will do that today and the remainder of the semester. It's a very useful tool for understanding things. And actually, the more you attempt to learn it and understand how to use it, the better you might be as a citizen, as a consumer of the world. With that said, we'll do an example, but does anybody have a question first? Comments? All 4 of you? All 3 of you, I guess, and me. That's why I dressed up today. I wore a hat because it's cold here, and I figured no one would be here. Oh, by the way, hold on. There is, before we move on, I should have noted, there's a slight typo here. This is not, it's the sigma. If you take the square root of the variance, that's the standard deviation. So it's this. Sorry. I will flunk my own class. Okay, so let's do some examples of this excitement, since nobody's talking. Where did it go? Okay, so what kind of questions can we answer using the standard, or excuse me, using these ideas? Let's do one. So here's our first example. So PennDOT which is the Pennsylvania Department of Transportation. Says the average age of a registered car in PA is 96 months. So that's 8 years. Oh. It is assumed the standard deviation is 16 months. So suppose we randomly select 32 cars. We want to determine the probability the mean, and particularly their mean age, is between 85 and 100 months. So does anybody have a question? Now you might say, who would want to do something like this? Well, I don't know. Maybe someone who does car auctions or sells used cars, who might buy them in bulk from auctions and other places, might want to ask a question like this. If I'm going to buy 32 cars from some lot, well, you know, what can I say about how old they're going to be if I don't go and pick them out? Okay, so how do we solve this? Well, we're going to solve it in the following way. So what we can use is we can use z equals x bar minus mu over sigma divided by the square root of n. And we need to do this for two z values. Remember, we want to know the probability that x is between two values. We want to know the probability that x is between, what was it, 85 and 100? Is that what I chose, I think? So as I did last week, there's a couple ways you can do this. You could just do the inequalities perform the algebra yourself, or you can calculate two different z values based on both x's. So let me maybe be a little more clear what my reasoning is here. I'm going to calculate two z's. So let's do it. For two different x's. For x equals 85 and 100. So we'll call the first one z1. That would be 85 minus, well, our mean was 96 over sigma, which we said to be 16, and then that's the square root of, what number did we say it was? 32? Yeah, 32. And so if you go to a calculator, you can easily compute this. I'll do that. So if you compute this number, you get approximately negative 3.889. And then my second z value, I'll do 100 minus 96 over this value. And when you plug it into the calculator, believe it or not, this comes out exactly to the square root of 2. Who would have thought? Which is approximately 1.414. So we can now calculate this. So if I switch colors, so let me remind you what the reasoning is. The reasoning is the probability we're after, which is the probability that the actual mean is between 85 and 100. Guess we can include these if we want. Now we know that that probability is equal to this probability. So it remains to compute this guy. Now there's a few ways to do this. You can go to a calculator on the internet and do it. Or you can use that thing I gave you, or you can look it up in the back of the book. Either way, if you go and do it. The one we were using before was that Z, it was, what was it? zscorecalculator.net or something. I don't care how you go about doing it. But if you do this, you get 0.92127 or $92. or approximately, there is a 92% chance that the car will be between 85 and 100 months old. Does anybody have a question? Comment? Does anybody have a question? So you need to know how to do these. We'll give you examples. And it's something that we should put a caution here, because the previous homework is slightly different, and that was the point I tried to implore to you on Tuesday. So,
Daddy,
yeah,
I thought you were watching
Lydia, I'm
show
busy right
at
now, honey.
time, but I really wanted to put Disney Plus on.
Sorry about that. Kids. All right, so we have two formulas. The first one we had is we had z equals x minus mu over sigma. This is for individual data. And then we had this one, and this is for what we call the sample mean. So you have to, when you're doing problems, you have to understand, what is the question asking? Is it asking information about one piece of data, like the last homework, all those questions were? Or is it asking about the sample mean, like this previous exercise was asking? So keep that in mind, I guess, is the best piece of advice I can give you. I mean, it's usually quite easy to figure out from the problem, because if they say, you know, if a sample versus a single, you know, if I say a random driver is selected, that's different than me saying 30 random drivers. So you have to look for these keywords that sort of spell out the situation. And we'll have that on the next homework assignment, and hopefully you'll work on those. And if you have questions, hopefully you'll ask. Okay. So what's next? So remember, what we've been talking about is the normal distribution. We first used it as basically a mathematical entity. Then we said we can use it to answer questions about, you know, certain scenarios. One other way we can use this is the following. So So what it can do is it can approximate binomial probabilities. In other words, the normal distribution can approximate the binomial distribution. Now, if you paid attention to the last class, we talked about. I said that the two legends, this de Moivre and Laplace, who really were I think they well actually they were the first. They were the first to recognize this normal approximation to the binomial distribution. And really, what this is this is in many ways a special case of the central limit theorem. So why would it be a special case of the central limit theorem? Well, these are things that I would ask you to think about. Now, before we talk more about this, let's think about why someone might want to use the normal approximation to a binomial distribution. You might just say, well, why would we need to approximate it? Why don't we just compute them? We had a formula for it. Well, there's a couple answers to this. Most notably, imagine before calculators, the binomial distribution had a couple very complicated things to compute. It had those factorials in it, and it could be very, very difficult, even with a handheld calculator. And so for a long while, computing binomial probabilities, the most efficient way of doing it would be to use the normal approximation. Now, you could argue now that because of computers that's unnecessary, but it still has some good uses. So that's what we want to talk about now. So that's what we're going to do. Okay, so let's suppose that x is a binomial random variable. So suppose we want to calculate the probability that it equals some number a. Okay, so let's remember what this means. What does this mean in terms of the definition of the binomial distribution. What does the probability that x equals a means? Well, let's write that down. You'll recall that this equals this scary thing, n choose a, and then p to the power k, and then 1 minus p to the n minus k. So let's recall what this means. This means how many successes do we get particular. Oh, I wrote that wrong. Hold your horses. I'm getting confused. Let me switch this letter. This is technically an error. Let me replace this A with K, because we used K earlier, so I shouldn't switch letters now. So this probability is one that computes what we have two outcomes. We have a success and a failure. And this is asking what's the probability if I try something n times, I have a success k times. Okay, so again, that thing in those parentheses, that n with a k over it, or excuse me, a k underneath it, remember, that's not a fraction. That's what's called a binomial coefficient. It has this meaning with these factorials in it. And what we'd like to do is we'd like to ask, how can we approximate this number? So using some fancy math, which we can't really do here, because it requires calculus amongst other things. What you can show is you can show that the probability that x is equal to k is approximately the probability of the following. X is between k plus a half or k minus a half Now, what is the difference between the probability on the left and the probability on the right? Well, this guy is the binomial distribution, so let's be very clear. And this guy is normal. Now, what are our parameters? What are our means? Well, what do we know about these creatures? Well, we talked about this briefly before. U has to be n times p. Sigma is equal to the square root of n p times 1 minus p. And then you also in order for this approximation to be worthwhile, you need n times p to be greater than 5 and n times q to be greater. Well, not q. I keep not using q. So provided that these values mu and sigma satisfy this, then we can get a good approximation. The following. So similarly, what is the probability that x, say, is less than or equal to k? Well, you just make the analogous. This is approximately the probability that x is less than or equal to k plus a half. You might be wondering where these halves come from. I'll explain that in a second. I guess I should go the other way here. So the 1/2 that shows up in all this is called the correction for continuity. And again, these terms come from a little heavier math terms. But one of the things that we need to understand, if you go back to a couple homeworks ago, I asked you this. The probability for the binomial is what's called a discrete probability distribution. That means it only takes on finitely many values, whereas the normal distribution is a continuous distribution. So if you were to graph the binomial, you get like a histogram. Whereas if you graph the normal, you get a smooth curve. And again, the mathematics behind that is a little beyond this course, but nonetheless, that doesn't mean you can't use it. So let's do an example of this. And if you have a question, please let me know. Be happy to answer it. Okay, so let's compute so let's say we're going to approximate. Well, let's actually set the stage. Let's be a little more clear. So get our calculator out, or at least our z-score phenomenal. Okay, so suppose guess I need my marker. So suppose x is a binomial random variable. With p equals a half. Let's determine the probability of 22 successes in, so how about 50 trials? So what are our values here? Here, k equals 22, n equals 50, and of course, p equals a half. Also, what values do we need? Well, in order to use the approximation, we need mu, which is n times p. Which in this case is 25. And what is our sigma? Well, that's the square root of np times 1 minus p, so that's 50 times a half, which is 25 over 2 inside the square root. So we could take and go get an approximation for that. On our calculator. So that is approximately 3.54. We'll round to 2. So notice that our NP is 25, and that is a requirement for this approximation to be sort of valid. So how do I compute this? Well, we go to the next page. We know that the probability that x is wrong button. So notice I want the probability of 22 successes. So the probability that x equals 22 is approximately, in the normal distribution, the probability that 22 minus a half is less than x is less than 22 plus a half. Now, in order to use my table, I have to convert to my z's. So we can rewrite this. This is 21.5 less than x less than 22.5. Now, how do we convert our x to z? Well, we have a formula for that. We've done it a few times now. So let's just remember what this creature is. If I come over here and do some algebra, you'll remember that z is x minus mu over sigma. We're not talking about means here, so we have this formula. And so if you do some algebra, that tells you that Z times sigma is x minus mu. And so if you do more algebra, you get that x is mu plus Z sigma. So if we plug that in to get our Z values, and what you'll notice, if you're paying attention, I'm now doing this a different way. So in all the examples we've done, I have sort of attacked the calculation differently. You need to decide how your mind best understands it. And so what is our mu? Our mu we already found is, so let's go back. What is mu? Mu is n times p, so that's 25. So this is 25 plus Z times sigma. Well, our sigma was 3.54 times Z, and then that's less than 22.5. So if we do some algebra here, what you get inside is Z. And what do you get on the outside? Well, on the outside, you have, if you just do the calculation, you have 21.5 minus 25 divided by 3.54. So you get negative 0.989. And then on the right-hand side, it's 22.5 divided by 3.54. And you're left with negative 0.706. And so the last thing you do is you go to your calculator to get these values. Again, I have zero care which calculator you use. I just hope that if you don't know how to do it, you ask either me or someone else. Okay, so when you plug that in, what do you get? You get 0.078. Or 7.8. Excuse me. Let's just leave. Well, I guess we could write it. If we wanted to, we can write it as a fraction. Or excuse me, as a percent. So what is that? As a percent, you move the decimal place over 2. So 7.8%. Now, what does this mean? Well, if we think about the original problem was we wanted to know what's the probability that we had 2 successes out of 50 trials. So if you put this into a real world problem, this would be, okay, if you flipped a coin 50 times, what's the probability you would get exactly 22 heads? So we can actually compute that if we wanted. So if you went and plugged it into a calculator and computed the actual value, so it was 50 trials, 22 successes. And so the exact value is, we got pretty close. We're accurate to 2 decimal points. So if you compare with the exact value, the probability that x equals 22 was 50, choose 22. P to the 22, which is not 22, it's actually, in this problem, we're using a half. And then this would be 1/2, because that's 1 minus the probability, and that would be 50 minus 22. And when you compute this, you get 0.07883, which is nearly exactly what we got with our approximation. So that's how you approximate the binomial distribution. Does anybody have a question? Any of the 3 of you have a question? All right, listen, we kind of need to end. I feel bad. I took took more time than I wanted to. Anyhow, if you have questions, please let me know. I am going to upload this. Hopefully more than a few of you will see it. It's actually a pain to upload these things, believe it or not.